Before I start my talk, I'd like to acknowledge my postdocs who contributed to this work and my sponsors as well. The outline of my presentation is going to be as follows. I'll give you first the background, then I'll show you some experimental data on thermodynamically supercritical flows. Very briefly then, the highlights of the governing equations, and then I'll treat two temporal configurations, mixing layers and boundary layers. Then I'll discuss some DNS databases on one species and mixtures of 2, 3, 5, and 7 species. The emphasis of the results is going to be composition influence, because in many cases, people just choose one species. The question is, having several species, a mixture of several species, does it influence anything in your results? Then I'll again go back to some experimental data trying to and I'll discuss that in a moment. And since here we are at a workshop rather than conference, I think it's very appropriate to have a discussion and questions to address future research. So the background is as follows. The motivation is really to understand whether high pressure turbulent multi-species mixing leads to either fluid interfaces or perhaps both, which we define as regions of very large density gradients. So the resolved scales must be of the order of the Batchelor scales, that's a mixing scale, or the thermal scales, both of which are smaller than the Kolmogorov scale. Or do we have, do we have material interfaces? Material interfaces, that means we have a phase change. And I talk here about a thermodynamic phase change. And then the resolved scales must be smaller than the Batchelor scale or the thermal scales. And I'll talk about the quandaries about that. So why are we interested in something like that? For example, we know that fuels are very complex mixtures of hundreds to thousands of species. Very impractical to model them or to derive some kind of physical understanding in a laboratory. So people use surrogate fuels. They basically take out a lot of the species, just work with a few of them, a mixture of a few of them, and then they derive conclusions. The question is, are those conclusions really relevant to the fuel that they started from? Then we're talking about reduced chemical kinetic mechanism. For hydrocarbon oxidations, these involve, I would say, at least 2,000 species and at least 10,000 reactions. So how are you going to deal with something like that in a simulation? Totally impossible. So people derive reduced reaction mechanisms. Chemists have somewhat of a different approach than other people in terms of deriving chemical reduced mechanisms. But basically the idea is the same. We just have a few species. So are those reaction mechanisms relevant? And then there is the pragmatic or expedient simplification. Well, you know, we take out the species we don't like. So it has also been suggested that material surfaces may develop at transcritical conditions, and I'll immediately show what that is. As their support from experiments or simulations for something like that, people have gone and published results in the Journal of Computational Physics. So they're going ahead and saying these things exist. The question is, do they exist? So here are some results from experiments. So at the top, these are the experiments of Polikov and Siegel for a fluoroketone in N2. So fluoroketone has a critical pressure of 1.87 megapascals, and each one of these results are at 2.08, 317, and 397 megapascals at a Reynolds number of the order of 10 to the fourth. And these are experiments where they were visualized. You can see these regions. What is plotted here is the magnitude of the density gradient, and here is multiplied by 10 to the minus 6. That's a kilogram per meter to the fourth. So you see these regions that are due to mixing of fluoroketone and N2. They are interfaces, fluid interfaces. okay? On the other hand, we also have results, earlier results from Oswald and Schick from experiments in fluids, mixing of N2 and then coaxial H2. And these were at Reynolds number of 10 to the 4th to 10 to the 5th at 4 megapascals. And what is plotted here versus the radial position is the gradient of N2, and here is a gradient of H2. Again, regions of high density magnitude in the flow. Now, more recently, there have also been some results published in Nature of Physics. So for those who are not familiar with the thermodynamic map, here it is. And these results were published for single chemical species. And they visualize and identify what's called the Widom line. It's a single phase regime, but if you cross from this side to this side, you go from a gas-like density to a liquid-like density. And this is what they saw. This is single phase, but you have fluid interfaces. Now, the question is, can we duplicate or can we see in our simulations results that are similar to what we see in experiments? So the conservation equations are the regular conservation equation, mass, momentum, energy, and species. We solve only for n-1 species because we solve the continuity equation. The only thing that I like to point out here are two things. First of all, the heat flux, Qj, and the mass flux, the capital J here, okay? Otherwise, U is the velocity, rho is a density, Y is a mass fraction, ET is a total energy. It's quite clear. The devil is always in the details. So we derive these fluxes from fluctuation dissipation theory. They're totally consistent with non-equilibrium thermodynamics and with the Onsager relationship connecting fluxes and forces. And what we use are the Stefan Maxwell fluxes. So the flux of mass, species mass, includes three terms. One that is proportional to the temperature gradient, that's called the Soret term. One that's proportional to the pressure gradient, that's called Barrow diffusion. And one that is proportional to all the gradients of the species, -1, like I said. And this is a mass diffusion flux. Now, the coefficients here are diffusion coefficients, and calculating these diffusion coefficients, you really meddle transport and thermodynamics. Let me give you an example. For example, for the Barrow diffusion, we use a partial molar volume. That's a thermodynamic quantity. For the mass diffusion, this is a complex equation, we use this quantity alpha d beta gamma, and that is computed from the chemical potentials. So this is a very complex case, and you can understand that high pressure thermodynamics will play very much a role in transport. Now, we also use a real gas equation of state. That's a Penck-Robinson equation of state, which is very nonlinear. We actually corrected because it's not always very accurate giving you the molar volume, but we corrected for that. And actually here you can see the quantity, the alpha d, alpha beta, computed from the chemical potentials. So let's look at the first configuration. This is a mixing layer. There is a mixture at the bottom, a mixture at the top. The mixture at the bottom is always of higher density at the mixture at the top. Doesn't make any difference because gravity doesn't play a role here whatsoever, okay? So these are the spatial and temporal discretization, time stability. The important thing is that we use here up to 7 species. Okay, if we use 2 species, we have heptane in the lower stream, nitrogen in the upper stream. If we use 3 species, we have oxygen additionally. If we use 5 species, we use additionally H2O and CO2. 7 species, we add CO and H2. The important thing is that on all these configurations, we make sure that the momentum ratio between the two streams is approximately the same so that we can compare apples to apples. What that means is that these additional species, except for sort of heptane and N2, etc., are trace species, which actually suits us perfectly, because what we want to see is what is the influence of trace species. If trace species are important, then obviously there's a lot to that, okay? So what we do is we put in a layer initially 4 vortices, we perturb, and we let the simulation go from a laminar to a turbulent state, a state with turbulent characteristics. How do we know that state with turbulent characteristics? We compute the spectra. They're smooth. They drop like a stone at the lower end at the high wave number, meaning that everything is very well resolved, okay? So I'm going to discuss results, but before I do that, I will give you here a direction on the legends. So the number 2 means 2 species, 3 species, 5 species, 7 species. R1 is a lower Reynolds number, R2 is a higher Reynolds number, and R3 is yet the highest Reynolds number. For the R3, whatever we compare here is a Reynolds number of 5,000, okay? But all of them have turbulent characteristics. Okay, P60 means a pressure of 60 atmospheres, P80 is 80 atmospheres. So basically, they're starting with just about the same composition except for these trace species. So if you look at the momentum, the growth of the layer, it's about the same. So dynamically, from the point of view of the dynamics, you can't see much of a difference. But let's look here at the positive span-wise vorticity that starts by being 0. And you can see that the Reynolds number, so the R1 is in broken line, R2 is in solid lines, and R3 here is in dashed dot, okay? So you can see that vorticity is very much affected by the composition, okay? Here is a lower Reynolds number, R1, R2, and this is R3 for the 2 species. So they're bunching, so the Reynolds number is very important, but it's not the same positive span-wise vorticity, and they're bunching according to the Reynolds number, but there's a diversion there according to the number of species. Same thing for the entropy, even more so for the entropy. So the question is why, okay? Now, let me show you why. We have high-density gradient magnitude regions that develop. So this is an X3 plane, okay? So see here, this is the highest Reynolds number. So this is on a log scale, and this is to 10 to the 5th. So these are very convoluted high-density gradient magnitude region. This is for 3 species, basically at the same composition, but a lower Reynolds number. These two are very comparable. This is 5 versus 3 species. So you can see here, we get practically the same thing. But if we look at them visually, we really can't tell much. What we have to do is do some probability distribution function and see how they compare. So here is a PDF according to the density gradient magnitude. We can see that we go to almost 10 to the 6. We can't say much here, but when we divide by the difference between the density of the lower stream to the density of the upper stream, we actually see them bunched. This is for the highest Reynolds number, the lowest Reynolds number, and these are the other two. We didn't plot all the results here. But people who believe that turbulence actually mixes, they're clearly incorrect, because here we have the highest turbulence case, and we have the highest density gradients. Why? Because the characteristic time of turbulence decreases, but the characteristic time of diffusion stays the same. So basically, within the characteristic time of the flow, there is not enough time for diffusion. That's why we get these higher density gradient magnitude regions. So what we see is that the initial Reynolds number has a most significant influence because they bunch with the Reynolds number, but the composition is the second most impactful one. And the question is, what is the composition of these high density gradient magnitude regions? Is there one fluid, or it's heterogeneous composition-wise? So here is for the 7 species, and we do some conditional averages, conditional with respect to the density gradient magnitude, and we find that actually these, when you go to the highest density gradient magnitude regions, all the species are basically there. And here it's actually amplified by dividing by the maximum mass fraction in the system. And that's for one case, but if you go and look at all the cases, that's exactly the same, okay? So these regions of high density gradient magnitude are the regions in which all the species are there. And the question is, if you're going to create real material interfaces, then you need to do the thermodynamics for all these mixtures of species, not just one species, because we know that thermodynamics, even if you have a trace species, that can actually influence the thermodynamic regime. All right. Now, there is another way to look at that, okay? And that's the behavior of the species in a mixture. And in order to see that, we created this non-dimensional or normalized variable that is the mass fraction normalized. So we actually computed the PDF of this variable. And if you look at it, if you look at N-heptane, and if you look at oxygen, we find exactly what we thought we would. The PDF, the values of the PDF stretches between 0 and 1, which means that you really get the values between the minimum and the maximum that you had originally in the mixture. Not so for the other species. You get regions that are smaller than 0 and larger than 1. For this, meaning that you have actually regions where the mass fraction is smaller than the minimum that you had originally in a mixture, or larger than the maximum you had originally in a mixture. This is called uphill diffusion, okay? And it's a phenomenon that is so prevalent that is used in industry for extraction purposes, okay? So it was first observed by Duncan and Tour in 1962, and there's a review paper here by Krishna, 2015. So let me show you what uphill diffusion is. I'll show you now some animations. The first one is for N-heptane that actually experiences regular diffusion. And the second one is for H2O that experiences uphill diffusion. For N-heptane, what you will see is that diffusion, the N-heptane goes from large concentration to low concentrations. For H2O, you will see originally is uniform. And from a uniform field, you form a non-uniform field. For those who think that we actually define entropy, production, and everything else, the gradients are very small, so actually they don't make a lot of difference. Everything is correct as far as dissipation goes and entropy production. Okay, so let me show you this movie first. What's going on here? Come on. I tried, it was working. Oh, goodness gracious. Okay, this one seems to be working, which is really the important one, okay? So you can see how you develop from a uniform field a non-uniform field. The other one was a routine one. So this is what uphill diffusion is. So the question is there uphill diffusion elsewhere too? I mean, that's a very important question. So let's look at boundary layers. We're having here either a boundary layer with a colder wall than the mixture or with a hotter wall, but in each case, the difference, the delta T, is the same. And we have a mixture of N2 and actually methane, and we're looking either at uniform or non-uniform mixtures to start with, okay? And here we are looking at a cold wall situation with a non-uniform mixture. Okay, goodness gracious. And we can see that there is uphill, this is a sketch of uphill diffusion. And we can see there is uphill diffusion here, here. I am not going to have much of a chance to talk about that because I see that I have only 5 minutes left. But all I want to show you is, here I'm plotting the mass fraction, the average mass fraction, as a function of y plus. If you have a wall at the same temperature as the fluid, the mass fraction stays the same. If you have a hotter wall, the mass fraction increases. If you have a colder wall, the mass fraction decreases. And we're starting here with a uniform situation. Now, so let's say some important conclusions from the studies that we have so far. So for free flows or attached flows, we see that there are fluid interfaces. Now, we also have seen that single species cannot portray mixtures, okay? And we've seen that because you'll never get results like that, for example, for a boundary layer, okay, that has a single species. And I haven't shown you that, but it turns out that the number of species also impacts the dynamics of the correlation between each species with temperature, which is very important for combustion. So the question is, what is the impact of these conclusions on the postulated existence of material surfaces where larger gradients exist? Is there phase transition? We know that in order to get any kind of interface, okay, whether it's a material interface or just any kind of interface, the first thing you need is a gradient, right? That's it, okay? But there is a more stringent situation for having material interfaces, and it's been postulated. So here, some experimental results, just citing some experimental results from a paper in 2020. Basically, it says there is ambiguity of shadow graphs. If you can actually see something, you may just see gradients, because what we're seeing is basically the existence of an index of refraction, right? This is what any optical system will see. Okay, so the description of the interfacial fluxes must account for interdependence of heat and mass transfer. We're doing all that. Now, here is a second experiment, 2022. And just to make it shorter, I like to read some of the conclusions. The results clearly demonstrate that what appears to be an interface and an image captured by an optical system whose spatial resolution is greater than the interface thickness is in fact an average high-density gradient magnitude boundary. Important information about the interface is thus inaccessible. This is clearly evidenced by the fact that the boundaries, which may on face value appear very similar, can in fact differ significantly in terms of their fluid interface and its scattering strength. So I have here some questions, some conclusions, etc. So liquid vapor surface interface thicknesses are of the order of nanometers. Okay, so to resolve these surfaces, we need to increase in part the resolution by order 10 to the 4. That's clearly unfeasible routinely. And I have even a question. It probably makes no sense to use a continuum approach because probably we can define a Maxwellian. So there are several other methods that have been used to actually capture interfaces. One is a Wino scheme, which we know is used for shocks. The other one is diffuse interface models, okay? For those, we need actually to have more than what exists right now. We actually have derived that. We need to have diffuse interface models for the fluxes of species and heat. But suppose that we actually find that there is, at a point in our system and our database, a thermodynamic change. Well, in order to have evaporation, we need a surface. How do we define a surface? And I don't know that, okay? I'm just throwing that out as a question. Okay, another way to do it would be to have molecular dynamics, but we need appropriate molecular potential for high pressure situations, and talking to Bill Goddard, that doesn't exist yet. And even if we had it, and if we did tabulations, that would be extremely expensive. So for the moment, that is not a solution. So here I have my last slide, okay? Discussion and open questions. How should we compute mixtures of species at the transcritical state, where maybe there can be, I don't know, because in a mixture of species, you can go from supercritical to subcritical without ever going through a transcritical space, because these are such complex thermodynamic systems that the phase space is so convoluted that you may never have to go through something like that. We actually did computations like that for drops and published in 2001. We were puzzled, and I never understood why. Now I do. And they were for a mixture of species. So how do we find, are we able to define what is it, material interfaces? Now for shocks, it's very nice. You can use either Wino or DIM, diffuse interface models. But for these mixtures of species, it's very important to know where that occurs, because for a shock, it doesn't change the thermodynamics of the system. For a two-phase flow, it does, okay? You get a two-phase system where evaporation may occur. So basically phenomena that wouldn't exist otherwise. So I am leaving this up here for discussion, and thank you very much for your attention.
Thank you. Are there some questions?
Thanks for the nice talk. Would you know why the density gradients are increasing with increasing Reynolds number?
Yes, that's what I said. They're increasing because with increasing Reynolds number, the characteristic time of the flow is shorter, right? But the diffusion time is the same. So by the time you get the flow to become what it is, diffusion can't catch up with it, okay? So that means that you're creating gradients, right? So that's the reason why, okay? So the disparity between the characteristic time of the dynamics of the flow itself and the transport time becomes larger. So it's basically like a shock. It's trying to get there, but you can't actually mix it in a shorter characteristic time that you have.
Are there other questions? Yeah.
Great talk. I just asked naive question. So this Kolmogorov theory of turbulence was developed for incompressible flows.
Exactly.
But you have two components, right?
It's a compressible flow, yes.
So there is divergence-free component, right? And then this gradient. So my question is, how do they, like if you look at them separately?
Well, just like you said, I think that there is generally a, how shall I say, people get attached to what they know. And they know Kolmogorov, they know incompressible flows. But then when you go to compressible flows like that, the criteria and the ideas that Kolmogorov had are not necessarily applicable, because here the Kolmogorov scale is not the smallest scale. You have to go beyond that, because mixing is a controlling thing. So the Bachelor scale and the thermal scales are smaller than that, okay? So dissipation, if you stopped at the Kolmogorov scale, you wouldn't get all the dissipation. These are direct numerical simulations, right? So you have to go beyond that in order to get the correct thing. It's not only compressibility, it's the fact that you get mixing. There are many reasons why the Kolmogorov scale is not here necessarily the relevant scale. Okay? I hope I answered your question.
Yeah, completely agree, yeah.
Okay, thank you.
I guess my question is, but yeah, if you split the field into divergence-free part and gradient parts.
I'm not splitting anything, because I think that everything is so coupled that if you split things, you're in trouble.
Yeah, because Kolmogorov in his original papers, he said it's for incompressible.
Absolutely, absolutely. He was an honest person.
So with that, let's thank Josette again.
Okay, thank you.